Hi, we're Group KKED.
I'm Diego.
I'm Kurt.
I'm Evelyn.
And today we're going to be performing activities for lab number 9, which has to deal with finding the coefficients of both static and kinetic frictions in two objects that we've been given. Let's get into it.
Now we're gonna set up our experiment, and now that we have our capstone open, we're gonna make sure that our blue card is open. But make sure you close the notifications. So this card is 447216. So now we're gonna make sure it's connected. Okay, so now we make sure we take off these two. And for the second one, we have to press the 0 sensor now. So now we can open our graph. And make sure it's the first one's gonna be position. And now we add our second one, which is gonna be force.
We're going to go ahead and start off with two things for our experiment, our cart and our mass. We're going to use a cart for position on our graph, and we're going to use this to measure the force applied to it. So if we go ahead and leave it here, and do you want me to put it? And apply a bit of force. We can see that on the graph, you can see position moving and the force moving as well. And we'll leave it there. And that's what we use to measure our kinetic and static friction.
Alright, so another important step of this experiment is actually finding the mass itself in kilograms, right, of the object that we're going to be pushing. So it's comprised of one, not only the block, but the weight itself. And so we start to measure it out, right? Let's see. So we've actually previously measured this, and we know that it's going to be 382 grams. This is our measurement. So now that we understand a little bit more about the experiment, let's get into the first trial. Diego over here is going to be the one pushing, and then I'm going to be recording the data and showing you how to read it. Ready? Hit record. Bam. And then perfect. So right there we'll hit stop. And so between the position and force graphs, we're going to get our multi-coordinate. And we're going to add coordinates to before it was moving, right? So let's say right about there. And then we'll add two more coordinates as it was in motion. So let's say right here, and finally another right there, right before it comes to a stop again. With these coordinates that we just placed down, we'll understand the force, right? As long as our coefficient, no, I'm sorry, as long as our force here is, oh no, we don't have the right there. So finally, the next step is to average out this values. And so we can get our highlighter tool, and between the two values that we just finished putting, we'll highlight, we'll hit this little signal, and then we'll finally find the mean. And we see here that the mean is supposed to be 0.75, and our force is 0.75 while in motion, and then our force while static is 0.83, and that checks out because as long as the static force is greater than the kinetic force, then you've done your experiment correctly.
So now we're gonna do our trial 2. We're gonna repeat the same steps for number 1. So now we're gonna get our points. So we're gonna start with our static point, which is gonna be at the beginning before we start the force. And then our second point is when our mass started moving. And our last point is gonna be right when it stops moving again. So now we can get our highlights, so we can get our average. We're all good because this one's bigger than this one.
We're gonna go ahead and start trial 3. And then we'll go ahead and do the same thing we've done for all the past 2 attempts.
So we'll get the coordinate sets of before, coordinate set of in between, and just before it stops moving. We'll go ahead and highlight on the other graph. Make sure you click this graph. And we'll get the averages of these. And there we have our mean and our other values.
So to jump into the calculations of both the static coefficient of friction and the kinetic coefficient of friction, we have to first, by definition, define what that means, right? We understand that the friction force itself has to be equal to the coefficient of static friction times the normal force. Similarly, if we were to draw like some sort of free body diagram where we have some sort of, let's say, mass, and that mass times its gravity, right? And then we have a normal force acting upon it. With that being said, right, here is our normal force. Here is our coefficient of either static or kinetic friction. And finally, here is our friction force itself. Another thing to note, our friction force, or specifically our static or kinetic friction, when we have some sort of static friction, that should always be greater than or equal to at least our kinetic friction. So because we're just going to be moving our object along a horizontal surface, right? And in this case, we are not going to have any angles, right? This is not going to happen. We can use the more simple version of the formula, where the coefficient of static friction is going to be equal to the force applied divided by the mass times gravity. And again, we'll just say that P is going to stand for the force applied. And remember, we're getting all these values themselves from the graph that we got. And so again, this applies to both our coefficient of static friction and our coefficient of kinetic friction. With that being said, if we try to, let's say, do all the static friction first, we got on our first several attempts, the force applied was 0.75, 0.83, and 0.68. To each of these values, we can go ahead and divide out our mass and gravity. I forgot to mention it earlier, right? But we will be assuming that our mass is actually going to be 382 grams. And our gravity is, as we normally use it, gravity is 9.8. And with that being said, we actually need to convert this to kilograms. So it's actually going to be 0.382. When we compute all of this, let's go ahead and compute these really quick. 0.75, divide that by that. That's it. For this first trial, we're going to get 0.2 as our coefficient of static friction. When we put in the 8.3, we will get 0.22. And finally, when we plug in the 6.8, we should get about 0.19. With that being said, we can now fill in our chart, right? Our first trial was 0.2, 0.22, and 0.19. We can use the, again, similar, where the force is applied in mass and gravity, to now find the kinetic coefficient of static friction. And for those trials, we got 0.70, 0.75, and 0.67. Again, now we can divide all this by our mass times gravity, still using the same mass and gravity as beforehand. And with these trials, let's quickly put them into the calculator and see what we get. So here we get 0.18, for our second one, we get 0.20, and finally, we get our last value of 0.19. Alright, so pretty similar values, right? These are our coefficients of kinetic friction. And the last thing they want us to do is just average these values, right? So let's see, 0.2 plus 0.22 plus 0.19, the average coefficient of friction for our static is going to be 0.203, and 0.18 plus 0.2 plus 0.19 should give us an average coefficient of 0.19. And so this checks out with our definition earlier that the coefficient of static friction should always be greater than that of the kinetic friction, further proving that we did our experiment correct.
So Evelyn, what's the importance of repeating these steps in our experiment more than one time?
So it is important to get more experiments because we can get more data and more results, so we can get a better and accurate result for the kinetic force.
Hey Diego, so what learning do you take from today's experiment?
We learned that static and kinetic friction affect motion, and we can measure it using the cart and sensors and Newton's laws.
How do you share your ideas to contribute to the design of the experiment?
So we all shared the idea to keep it as a flat plane instead of an inclined plane, just so that we wouldn't have to be dealing with any angles in our calculations, and it makes the experiment just a little bit easier.